Now, so far, I've followed kind of close to the order of the textbook for chapter 22. Talked about electric field, definition of it. That's mostly section 1. And then adding of electric fields, because electric fields are vectors. And so we found the electric field of a point charge and the electric field of a system of point charges. That's pretty much section 2, 22, section 2. Rather than doing 22 section 3 right away, what I'm going to do is I'm going to skip to section 6 because it makes more sense, and then the intervening sections are actually more complicated. And so what I'm going to do is I'm going to do the simple things first and then kind of work our way up progressively more complicated, rather than just jumping straight into the complicated then back to the simple. So what I'm going to do is I'm going to jump now to section 6. So let's do a quick little example. Let's say that we've got a metal plate and we have another metal plate, and I want an electron to come loose from this plate, and I want the electron to go shooting to that other metal plate. And let's say the separation between the two plates is 1.25 meters, and I want it to hit the other metal plate. I want the velocity when it hits the other metal plate to be 2.14 times 10 to the 6 meters per second. So I want to know the direction and magnitude of the electric field between those plates such that when it hits with that velocity right there. Okay, so that's what I'm after. I want to know the direction and magnitude of E. Okay, so you think about it, and now this is actually something that was done for a long time, and that was in tube technology. So for a vacuum tube or something, you would actually heat up a metal plate. Electrons would come loose. They'd go shooting off to another metal plate and carry energy between them, depending on various parameters. You could either make them go or not go, so that it would act similar to a transistor, or you could actually make the current go one way and not the other way, so to act like a diode, or you could actually amplify signals with it. And so that was used in tube technology and in cathode ray tubes. Old TV computer monitors would use this, and they'd have a little hole in the other plate for the electron to go shooting through and then direct it off to a screen. So this was technology that was very commonly used. It's still used in X-rays machines, because what you can do is accelerate electrons at very high speeds, and when they slam into a metal plate like that and stop, they produce X-rays. How they do that's a little beyond the level of this class. There's actually 2 different ways they do it, but this actually is used in X-ray devices today as the primary way of making X-rays. So you need to be able to do this. So I want to know what's the direction and magnitude of the electric field. Okay, well, first of all, I want the electron to go to the right. So that means the electric field has to be going to the left, because electrons are negatively charged, and that means they have a force exerted in the opposite direction of the electric field. We know the force is going to be QE. So in that case, it's going to be minus EE. So if the electric field is to the left, the electric field will be negative. Negative means positive, so a force to the right. So we also know that force equals mass times acceleration. Therefore, mass times acceleration, I'm going to absolute value now, EE. Okay, and so we're trying to find the electric field, and so that's going to be mass times acceleration over E. Well, we know the mass in electron. Mass in electron is 9.11 times 10 to the minus 31 kilograms. That's a known quantity. Fundamental charge, 1.602 times 10 to the minus 19 coulomb. Another known quantity. All we got to find is the acceleration. So how do we do that? Well, physics 1. The electron is starting from rest, so V naught is 0, and it ends with a certain known velocity over here. the final velocity is 2.14 times 10 to the 6 meters per second. I gave you that. And so how do we figure this out? Well, you remember from Physics 1, x equals x naught plus v naught t plus 1/2 a t squared. If I put my origin right here, that term is 0, v naught is 0, so x equals 1/2 a t squared. We know that the final velocity is v naught plus at. Initial velocity 0, so I can do some algebra and say t equals v over a. So if I plug that into the other equation over there, x is 1/2 a v over a squared, or in other words, v squared over 2a. So a is going to be v squared over 2x. Well, we happen to know what x is. Okay, so this is going to be equal to 2.14 times 10 to the 6 meters per second, that quantity squared, divided by 2. We said that was 1.25 centimeters, so that's 0.0125 meters. And so the acceleration is 1.83 times 10 to the 14th meters per second squared. Okay, and we had already said that E equals ma over E, so we just plug in those numbers. 9.11 times 10 to the minus 31 kilograms times the acceleration we just calculated, 1.83 times 10 to the 14 meter per second squared. All that divided by the fundamental charge, 1.602 times 10 to the minus 19 coulombs. And the answer is 1,040 newtons per coulomb. And so that would be the electric field. And the direction of the electric field, the electric field vector would have to be newtons per coulomb in a direction along the minus x-axis. So in other words, it has to be directed to the left as it was drawn. Okay. So you could say the angle was 180 degrees from the positive x-axis. You could say it's to the left. You could say it's the minus x-axis. I don't care how you say it. All three of those ways of saying it say the same thing. It says the direction that it was pointed. You could even say it was directed towards the original plate. Okay, so that would have been acceptable as well. So all I asked was the direction and magnitude, and so the 1,040 newton per coulomb was the magnitude, and you somehow have to tell me what direction is. And I'm smart enough to figure out all three of those ways of saying it mean the same thing. So on a test, I'd take any one of those.